Good morning, everyone, and welcome back to robotics. So this week, the thing that I want to talk about is the upcoming assignment where you will be taking your mapping robot control program for homework 6 and extending that control program to do pathfinding using astar search. So astar search is a neat sort of graph search algorithm that is especially commonly used for pathfinding in robotics or game AI or wherever you need to sort of find a path on a map. And the thing to compare it to is Dijkstra's algorithm. And I found a neat thing here that does exactly that visualization. So here we have some grids. Let me go ahead and densify up the grid a little bit. But here we have a pair of grids. And we're going to go ahead and generate. It's the same map on both sides. So here on the left, we'll be doing astar search. Here on the right, we'll be using Dijkstra's algorithm to find the same path. So then we can set our destination here as being this red dot up in the corner. You can see that appeared on both maps. And then if I go ahead and click over to path search, I can go ahead and pick some location. I'll pick this square here, and it's going to start executing the search algorithm. And you can see that astar found the path super fast, and Dijkstra is still sitting here looking. And the reason for that is the key difference. Oh, and Dijkstra found it. So the way Dijkstra works, if we go ahead and run that again with a new path, is Dijkstra is going to take the starting position, look at its neighbors, and ask, did we get where we're going? And for each of the neighbors, it's then going to keep track of how we got from the starting or from the previous cell to the neighbor. So let me crank this up so that I want giant cells here. There we go. Go ahead and make a map, generate map. All right. Generate another map. Again. All right, there we go. So let's do this. There's our destination. Here's going to be our start. And they both did it pretty quick. But here with Dijkstra, if we're starting at the green dot, the first step that we're going to do is we're going to look here, and look here. None of them are the destination. But we're going to have a data structure that's going to keep track of the previous cell. So for each of these 3 cells, the previous cell was the green one, the starting position. So then for each one of those, we're going to look at their unvisited neighbors. And so we need to have some sense of which cells are blocked and which cells are open. But if we're considering this cell here and we're going to look at its unvisited neighbors, that's just this one. So we'll look, it's not the destination, and we'll go ahead and mark this cell as having a previous cell of this cell. Eventually, so our destination was here. Let's go ahead and search from here. Eventually, we go ahead out and get to our destination. And then we can just walk back and say, okay, this one knows its previous cell, it was here. This one knows its previous cell. We walk back, and Dijkstra's will find the shortest path because we're effectively doing a breadth-first search of the graph. And once we get to the destination, we know that following those previous pointers will get us back to the source following the shortest path, because if it wasn't the shortest path, we wouldn't have found the destination yet, because we're finding in each sort of iteration of the search algorithm, we're expanding out and looking at paths that are one longer. In contrast, the way astar works, let me go ahead and put down a destination of here. Then we're going to path search from here. The way astar works is it's going to first try going straight towards the destination. So we know we have a heuristic function that we're using to decide which sort of paths we're going to look for first. And we have the sort of coordinates of the destination. And so if we're starting at green and going towards red, the first thing that we're going to check is if we go in the direction that's generally towards the destination, does that get us there? Then we're going to expand its neighbors. Does that get us there? We expand its neighbors. Does that get us there? And we're going to expand out until we finally get to the destination. But we will always expand the sort of unexplored cell that is closest to the destination. And that will result in us potentially being able to find the path without actually exploring the whole map. You can see in dijkstra's, we ended up having to explore this sort of like bottom quarter, bottom third of the map here. And over on the astar map, it's not purple. It wasn't explored at all. So that's why we're using astar. It's a potentially, if this isn't a maze, and we don't have to do a lot of backtracking, it'll let us do our shortest path search in linear time in the length of the path, as opposed to sort of linear time in the number of cells in the map. In Dijkstra's algorithm, we sort of n squared in the length of the path. We end up having to search a circle from the start location all the way out to our destination, and potentially further, all the way out to sort of the furthest point on the path, and then back if we have to loop around. But kind of this is sort of an n squared sort of situation. This is an n situation unless we produce worst cases, and in a worst case, they're both going to take, exponential time if we had a sort of a more complicated map where we could actually have a exponentially complex graph. On this sort of two-dimensional map, how complicated it can actually be is limited. I think quadratic is sort of the worst it ever gets. Alright, so that's our introduction. I'm going to post some other resources about astar search. The resources are so good that I'm not going to actually directly explain it. You can go ahead and look at the research, resources, but astar search is what you're supposed to be implementing. Oh, and sort of the general strategy in having the robot follow the path is that we use astar, and we're going to assume that in our occupancy grid, cells that are unknown are unoccupied, and that'll let us produce a path that's sort of straight towards the goal. And then we'll have the robot follow that path. We'll want to have like an obstacle avoidance, fast, tight loop control routine that's going to like point the robot down the path, and we drive down the path. And as we drive down the path, our laser sensor is going to find out that, oh, actually there was a wall in the way, we can't go that way. So then we rerun the astar algorithm. We can just rerun the astar algorithm repeatedly in like its own thread. But we end up rerunning the algorithm with the new information, and that tells us, oh, the new shortest path is we're going to try to go around the wall because we haven't seen whether the wall extends up or down, and so we'll go whichever direction looks shortest. And this will result in the robot sort of doing a optimized-ish exploration of the map, kind of like the original astar path. Alright, so that is the upcoming homework. Good luck and have fun.